So I just want to talk today about the remainder theorem and the factor theorem and how these are related and what they have to do with finding the zeros of polynomials, which is going to be our next really big topic. A really good understanding of what the remainder theorem and factor theorem say, and more importantly, why they're true, is going to be really, really important for finding out the zeros of a polynomial. So to start out with, let's go ahead and just look at what the remainder theorem says. The remainder theorem says that if a polynomial p of x is divided by a term x minus c, and c can be any number, fraction, whole number, whatever, then the remainder equals p of c. In other words, if I divide a polynomial, the remainder that I get is going to be the same as if I had plugged that number into the actual polynomial itself. And so this is kind of a strange theorem, but the reason it works is actually pretty simple. It looks a little complicated, but it's not too bad. So first I'm going to go ahead and just do this, see what I get, and then show you why that's true. So we have the polynomial 2x squared plus 7x plus 7, and we want to find p of negative 2. And so to do that, we're going to divide our polynomial by x plus 2. And because these are always going to be these nice linear factors, we're going to use synthetic division. So negative 2 goes in there, and then we write down our coefficients. And we're going to go ahead and do synthetic division. So we'll drop the 2 down, multiply, add, multiply, and add. And that last term is our remainder. And so what this tells us is that since we divided p of x by x plus 2, that the remainder that we get is equal to p of negative 2. And so now we know that p of negative 2 is equal to 1. And we could verify that by plugging in negative 2 for x squared if we wanted to, and you can check that out on your own. But you'll see that p of negative 2 is 1. Now that kind of seems very strange. Why should that work? And it has to do with the way we write this polynomial out and what the properties of division are. So this is 2x plus 3 with a remainder of 1, which you can write as 1 over x plus 2. And so let's go ahead and take a look. With numbers, I'm going to take a look with numbers first, and then we'll go back to this example. If we have a fraction, let me use a blank sheet of paper here. If we have a division problem like 16 divided by 3, we can write that as 16 divided by 3 equals 5 plus 1/3. In other words, the quotient, our number divided by our divisor is going to equal our quotient plus our remainder over the divisor. We kind of like this, it's kind of like a mixed number, 5 1/3. But we could also write this, the same exact fact, written in a different way, that 16 is equal to 3 times 5 plus 1. And if you look, we've got the exact same things. We've got our dividend, we've got our divisor, our quotient, and our remainder. So they're just written in two different ways, and you can verify that this is true simply by taking both this equation and multiplying by 3 on both sides. When you distribute it to all three terms, you'll see that we get this fact here. And so in the polynomials, we'd call that p, that d, that's q, and that's r. And by multiplying by 3, now we have p, d, q, and r. Or our product, our divisor, our quotient, and our remainder. So let's just take a look at what that looks like in terms of polynomials. So here we have the expression that we just looked at. We took 2x squared plus 7x plus 7 and divided it by x plus 2. So that's our polynomial. That's our divisor. And when we do that, we get the quotient plus the remainder divided by the divisor in that mixed number form. And the same thing we can do up here when we multiply this whole thing by the 3, we can do the same thing over here and multiply this whole thing by x plus 2. And if we do that, we're multiplying this whole thing by x plus 2 and distributing it through, we get the exact same expression written in this product form. And it says that, it's just another way of writing it, 2x squared plus 7x plus 7 is equal to x plus 2 times 2x plus 3 plus 1. In other words, the product, or the original polynomial, is equal to the divisor times the quotient plus the remainder. And if you were to multiply this out, you'd see that's true. And what we really did here is when we divide a polynomial, we're pulling out that x plus 2 and we've got that remainder left over. And so this is just another way of writing that expression. But here's where we get to why the remainder theorem actually works. If we wanted to find p of negative 2, we could plug it into the original polynomial, or we could plug it in to our new polynomial, our new version of the polynomial, with that x plus 2 pulled out. What's really nice is what happens right here. If I plug in negative 2 to this x plus 2 factor, it goes to 0. Which means that whatever this is multiplied by 0, so it doesn't matter. And we're left with just the remainder. And that's going to happen every single time we use this remainder theorem. Because we use that, we pulled that factor of x plus 2 out, it's always going to be 0 when we plug in negative 2. In general, with the remainder theorem, when we pull out that factor of x minus c, you're always going to have that factor that when we plug in c is going to give us 0. The only thing left is going to be that remainder on the end. Now, when that remainder is equal to 0, we have what's called the factor theorem. And the factor theorem is the really